So just a little bit about the consortium this morning. The consortium was set up now just about 2 years back, with real work getting started in 2019. And it was initiated through a solicitation by the Department of Energy. And DOE's goal was to facilitate a nationally focused not-for-profit organization that worked within the industry and prioritized R&D activities that reduce the LCOE for offshore wind in the U.S. and maximize other economic and social benefits. Our impacts are to promote innovations that are responsive to technical and supply chain barriers, to help that are faced by offshore wind project developers in the U.S. We want to help build strong networks connecting the industry. Excuse me. Hold on 1 second. I'm not quite sure what happened here. There we go. Excuse me. We want to build strong networks connecting technology innovators and investors in the industry and increase U.S. content and job opportunities. The administrator initially was New York State Energy and Research Development Administration, and they, NYSERDA helped sponsor half of the funding for the initial consortium, which totals $40 million, $20 million coming from DOE and the remainder coming from NYSERDA. We also have the participation of several key states, Maryland, Virginia, and Massachusetts, that are contributing to our funding and our effort. The administration of this consortium has subsequently been turned over to a 501c3. That includes myself as the executive director, and we have 2 staff members that are helping to coordinate our R&D efforts across the country. Right now, our duration under the current funding is for 4 years, but we expect that funding to continue well into the future, and we'll continue to fund R&D efforts throughout the next decade. And I think someone else has control of the slide, so thank you, Michael. Just a brief overview of what we've been up to at the consortium for the past year and what we plan on doing in the short term over the next year. So first, many of you know a solicitation was issued last summer by NYSERDA promoting research and development efforts in offshore wind. That was guided by a roadmap that was designed by the consortium, which contained 3 pillars of focus: offshore wind plant technology advancement, offshore wind power resource and physical site characterization, and installation, O&M, and supply chain solutions. And underneath each of these pillars, you see the detailed challenge areas that were crafted in that solicitation. The solicitation was closed on December 31st of 2019. We received an overwhelming number of proposals, which are currently in review. To date, we've made 8 awards, and these are listed here at the bottom. And those awards have been made and announced and are currently in process. We expect to make additional award announcements by the end of, probably the end of April, beginning of May, mid-May. We'll be announcing additional awards related to that solicitation that was closed in December. In parallel to that, we are thinking about what our next solicitation looks like, and we expect to issue a new solicitation probably sometime in the middle of this summer. Of course, current events are impacting our timeline a little bit, and we're cognizant and sensitive to demands on everyone right now that are, might distract a bit from some of our efforts, but we are keenly focused on issuing another solicitation in the middle of this year. That solicitation will reflect, again, the roadmap, which is available on our website if you haven't seen it already, and will be similar to the solicitation issued last year, but we'll probably have some tweaks to it and a little bit additional focus on areas where we may have not received a considerable number of proposals, or areas that have been identified by developers and our other consortium members as being extremely important to the next round of R&D efforts. And one area that I want to highlight that's a key area of interest that was identified in our roadmap in the last solicitation, and certainly on our minds for the next solicitation, is power system design and innovation. And that is why today we wanted to host this webinar. And while the study that you're going to hear about this morning from Jessica is not an award that was made through the solicitation. I think the study was done prior to or overlapping with the solicitation. The area that NREL and Jessica has focused on really highlights some of the issues with power system planning and grid integration. And we wanted to take the opportunity to hear more about some of the work that NREL has done in this space. So before I turn it over, I just thought I'd talk for just another 30 seconds about kind of a little bit more details in this area. And again, the main challenge in this area is, as I said earlier, with all our challenge areas, is to reduce the cost and risk of bringing electricity to land from an offshore wind plant and distributing it into the grid. Uncertainty about this interconnections can raise contingency and finance costs and make array cabling much more expensive. So our goal at the consortium is to think about that and do research in those areas that would help reduce those costs and accelerate technology. So Jessica, why don't we, I think you have control now, why don't we go to the next slide and I'll just take a minute to introduce you before you get started. Thanks. As I said, the consortium often works with the National Renewable Energy Labs, and although we did not fund this specific study, we work with them quite often on a number of different efforts and wanted to highlight this research area in particular. So Jessica, thank you for joining us this morning. I'll just do a quick introduction. Jessica Lau is a Senior Technical Program Manager at NREL and specializes in power system planning. She leads research to understand and improve reliability and resilience in power systems through data, modeling, and analysis. Her experience expands renewable integration, wholesale electricity markets, transmission and distribution grid modernization, next generation system planning, and utility distribution planning. Her previous roles included work at the ISO New England, Independent System Operator New England, as well as Orange and Rockland Utilities in New York, where she studied grid integration and grid modernization. And then finally, Jessica holds a BS in electrical engineering and math from the University of Massachusetts Amherst and an MS in power systems management from WPI, or for those of you not from Massachusetts, Worcester Polytechnic Institute. So Jessica, why don't you go ahead and get started? And I think you have control of the slides.
Great, thanks so much, Carrie. Hi everyone, this is Jessica Lau here. Thanks, Carrie, for introducing me. So what our plan is for about the next half an hour for me to walk through the slides, and trying to wrap up about 40 past the hour, and then have an open forum for us to discuss. So I think we're taking questions through the chat box, so I may have limited ability to see that chat box while I'm presenting, but for sure, we're at the very end, we'll definitely come back to it. So in that case, let me kick us off here. Again, I am from the National Renewable Energy Laboratory. We are located in Colorado in the United States, which is kind of, if you were to point at a single point right in the middle of the country, that's roughly where it is. We are the only national laboratory in the US with its sole mission focused on energy efficiency and renewable energy. So that spans from the foundational science to R&D, to discovery and invention of methods, to components and energy delivery systems. That's often done, of course, not in isolation. So we have extensive partnerships across the world in what we do. So it's, sometimes we're known for what we do, and people think, oh, you must only do that in Colorado or in the US, but we work extensively throughout the world because of our mission. So another part I'd like to highlight today is that because of our mission within renewable energy, very early on, it was established the National Wind Technology Center to be part of NREL. So that was established in 1977. It's a site a little bit called the Flatirons campus, a little bit south of Boulder, Colorado, if you've heard of there before. And in the picture, you can see that what I call to be, the awesome toys of the energy laboratory is that, some of the funnest things to do for researchers is the ability to partner with different turbine manufacturers and really study the different components and their operations and how to plan for them. And so you can see that, in our wind component testing, certainly for blade testing, dynamometer, drivetrain testing, things like that. So it's, although we focus on all the different technologies in renewable energy. Wind is certainly one of our favorites and one of my focuses as well too. When we think about transitioning to offshore wind, there have been, of course, many different studies and events and different guidelines, I think, throughout the years. The biggest part of what NREL does is certainly to support the Department of Energy in the US. Let's see if I can just scroll down a tad bit here. Oh, having fun here. There we go. Cool. And so, for different type of wind visions, the National Offshore Wind Strategy, we've seen numbers ranging from low to high, right, like such as 86 gigawatts in all regions by 2050. And since you're joining the webinar today, if you're familiar with offshore wind, you know that even through the years, right, even the difference between today and maybe 3 years ago, I think our projections and reality of offshore wind has consistently evolved through time too. So with just highlight some publications through Department of Energy, certainly there was the Wind Vision, which had a component of offshore wind in terms of where they saw the future to be, as well as the National Offshore Wind Strategy that you can find that was published in September 2016. And what we found was that with the motivation of the different challenges and visions of the future that they published here, what NREL was asked to do by DOE was to conduct the study I'm sharing with you today, which is specifically focusing on the offshore wind resources in the Northeast. So in the US, that would include kind of New England area, which is the 6 states here, as well as New York. In this picture, it's a little bit cut out here. It's the reason behind that is because in the US, there's substantial offshore wind potential in this region here. And the different price declines throughout time and eyeing those different BOEM sites and leasing sites offshore certainly have invigorated this to be a high potential impact into the energy and grid system within the Northeast. And sometimes we get the question, well, why the Northeast, and why did you start there? And so to zoom out a little bit, showing you this whole map of the United States here. That region we were just talking about is the Northeast here. So certainly in terms of a heat map, the darker the color for offshore, the higher the wind speed is that we've historically seen. And so, you can really see that the darkest color certainly is here and maybe only comparable to this area in the Pacific Northwest here. This is the region we're going to focus and talk about today. Okay. Now, in this particular study, what we looked at, of course, is different interconnection points. Of course, it's one of the most important things about when studying offshore wind is, hey, where are you going to connect the offshore wind turbines into and inject the energy there? So what we did here, certainly on the right-hand side, you can see that I'm showing the different points of interconnection we're using. The way that we arrived to this was looking at all the current BOEM lease area and call areas within the Northeast region. So this spans all the way up through Maine as well too. And we looked at the economic viability. Sorry guys, I'm having not the best in this PDF here. There we go. So the economic potential, if you're interested in the detailed methods of that, I've made a citation here. In short, we take a look at historical pricing of LMPs of electricity at the bulk wholesale level, and we make determinations of how good the wind speed is paired by historical pricing to make an initial assessment about economic viability. So within those lease and call areas, we essentially ranked the wind resource from best to worst. So when we think about interconnecting the first 2 gigawatts, I'll go through the scenario shortly. Those are going to be the highest economic viability that we ranked, and then slowly adding on. Now the particular substations we're looking at here, we've considered only existing 345 kV buses and any scheduled generator retirements by 2024. Now, I think some of you may say, well, hey, can't we build a new substation? Or, I think maybe we can connect into 113 kV too. And to that point, I would completely agree with that as well. For this particular study, we are taking the minimum upgrade approach, which means, hey, what is the lowest hanging fruit and the quickest way in? I think, certainly a point to, if we were to interconnect increasingly more and more offshore wind, I think looking at it at a more holistic approach, such as looking at all the wind that may connect, I think in the different states coordinating with each other would certainly be the more likely, technically efficient way. Let's see. So for this, now that we looked at the interconnection points, so for the study background, we're going to start from left to right here. So what we looked at was 3 different levels of offshore wind capacity added to the Northeast region. Now, when we do studies like this, a lot of times it's to think about not exactly to look at the results and say, hey, like if you add 2 gigawatts, this is exactly what's going to happen. These type of studies are really more to inform like what is the potential impact, but also the magnitude. So I would take all the results and numbers we're going to go through as, what is the relative difference between 0 and 2 and 2 and 7. More so than, oh, hey, they said it's going to be 10%, and I'm going to write down that 10%. So that's a little caveat there. But we did the 3 different capacity levels within the Northeast. And what we did was to plug that into a power system operational planning tool, which is a production cost model called Plexus that we use here, as well as looking at their resource adequacy, another metric of reliability in the electric grid. And so with these 2 different models and all these different inputs, such as, a full nodal representation across all the generators, so not just offshore wind, but, renewable energy, thermal units, the total transmission network, how does load operate within these years, and certainly any retirements to be expected with offshore wind data, right, in interconnection we talked about here, that magically, with this arrow here, plops out your magic outputs, which is the key performance indicator. So we've listed many of the metrics that I've shown here, and I'll be going through it at a high level today as well. One of the things I did miss out on telling you all about is that the study here has been published, and the link was on the title slide, and I'm sure we can follow up with the official link in an email too. And so that report has a lot more detail than what we're going to go into today. But let me dive right into our results, because that's what you guys are here for, right? You want to hear what is the initial findings. So we're going to first start at generation impacts. Again, we're adding 0, 2, and 7 gigawatts of offshore wind of nameplate capacity within the model here. And it is assumed at $0 per megawatt hour. So consistently with other wind and renewable energy sources like solar, where we are assuming, their cost is near 0. Again, I do understand that, in reality, perhaps there is negative and positive dollar bidding as well. But in this study here, we are making a flat $0 per megawatt hour. And what we find is that in New England and New York, they remain as net import regions. Now, this is really important for the Northeast because they require a lot of energy to be imported, meaning transferred through transmission lines, injected into their area. And that's that we're going to continue seeing that to be the case, even with the injection of more energy here. It is, as you saw geographically, it's kind of off into one side, so it does have limited ability of transferring energy in. What we see is because of the injection of offshore wind, we find that some of the natural gas combined cycles are decreasing their generation, since you have that $0 per megawatt hour coming in, the cheaper resource, then this natural gas here is a little bit less. In terms of curtailment, which is kind of sometimes a signal for the health or balance of the grid system, what we saw is that we range from near 0 to about 2% different curtailment. So even in our highest offshore wind scenario, which was 7 gigawatts here, we saw about a 2% a reflection there. And the other thing too, of course, is, people often talk about the variable nature of renewable energy. And so, one of the things we saw here is that with offshore wind in a larger amount, like 7 gigawatts, is that, that kind of variability over time leads to other units responding flexibly. So units like natural gas combined cycles or combustion turbines that we saw, let's see. So for natural gas combined cycles, we saw that they had increased starts and decreased hours online per start. And for natural gas combustion turbines, we saw that they had decreased amount of starts and also decreased the amount of overall generation. So, this, of course, when you add one thing into the system, you will see that other components of the system will change as well. Okay. Now we're on to cost. And as we go through the slide, again, I want to remind everyone that we did assume that offshore wind, land-based wind, and solar resources were modeled at a zero marginal price, which means that they're actually competitive or competing against each other too. So when you look at it, a lot of it comes down to location, congestion, things like that. And of course, the resource availability, not to miss out on that. The production cost here is a reflection of what it takes the electric grid to produce energy. So I would say, simply saying, the production cost is one part of the total cost of operating grid. It doesn't include any costs like interconnection costs, right? When we talked about earlier, hey, you're adding 7 gigawatts, so that's not free. Well, it's not, this particular cost is just about generating energy. It doesn't include any costs about connecting or the technology costs either. But what we see here is that in the, this is a comparison from, we're going to start on the left side here, or on the top side here, is from, the base case, no offshore wind to 2 gigawatts. We see that the production cost change decreases about 5%. And again, that's because, you're injecting offshore wind. It's modeled at $0. So essentially the system is seeing it at $0. And when we add more, 7 gigawatts compared to, the 0 gigawatt no offshore wind case, it is at negative 16%. So we're starting to see some higher numbers, right? And when we fold in, I pointed out earlier, imports is a really important thing because you're typically paying for energy that you're importing too, right? Nothing is for free. So this would be just a local Northeast cost decrease here, and this one here reflects, if we assume a standard cost for the imported energy, you'll see this sticks around about the same at 5%, and this gets into a negative 19%. So when we think about driving home cost-benefit analysis, this study is not a full cost-benefit analysis, and I would say that, if people were interested, it's to take a look at these numbers, add in the cost of what it takes to interconnect, site, the technology costs, installation costs, adding all that back in to weigh what this looks like. And this cost here is a representation over a year. And again, it's just comparing to, no offshore wind versus offshore wind. As we know, the resources are very weather dependent. If we look at historical years, we would even say, hey, depending on the year you look, hey, maybe some years are good wind years and some years are, lower wind years. So I would say that what we did here was use a historical 2012 load, wind resource, solar resource data here. So it is, with kind of consideration, I would encourage that is, this is based on 1 year's of number, and looking across many different years, adding some different ensembles about what the wind might look like, as well as other contributing factors like load and things like that, would be really, really important to add a variety of these statistics together. Okay. All right. And as Carrie's intro earlier, I am a power system planner, and so reliability is certainly always top of the mind. So what I'm showing here is about a resource adequacy. So I mentioned earlier, this is a metric about the reliability of the system. It is one of the metrics, and it is very commonly used across a lot of the independent system operators around the world for this as well. And what it really asks is this key question here: will the resource be there when we need it? Right. This is that variability I mentioned earlier. A lot of times, you know, some of the questions are like, well, hey, like I can't just dispatch the wind to turn on. So what does it look like? But I think what we can do is to take different modeling, different methods to at least assess, like, what does it look like? So I think this is probably one of the most interesting findings that we looked at this study as well. We did use a NREL design model. This is open source, by the way, so that's available. And we used a few different metrics, but for our discussion today, we are looking specifically at the loss of load expectation here. And in the report, you'll see capacity value numbers as well. Now, I'm going to start from left to right. Now, in the reference transmission and interconnection, meaning, again, we reflect all the different transmission and we look at the interconnection points specific to the lower New York region. What we saw in the few different cases is that the loss of load expectation, which means what is the expectation that you would lose load? So meaning maybe brownout, blackout on the bulk system level. So not a distribution, but bulk system. We start to look at, hey, 0 gigawatts, 2 gigawatts, 7 gigawatts. And you know, the first time I saw these numbers, I bent over, I looked really closely, and the team said, oh boy, did we just run the same case 3 times? Or did we make some error in the input data to make these numbers exactly the same? Because what you're seeing here is that hey, the reliability does not change no matter how much wind is added into the system. So you have to say, well, that doesn't sound right. I mean, it should at least be impacted in some way. And I would point out that although there are some differences, this is statistically indistinguishable since there's lots of decimal points here. So we said, oh, okay, that's interesting. Let's run some more cases to see, you know, what is going on here. And so what we started to see was that, you know, the transmission system inland between, this is New York here, Long Island, and this is the 5 boroughs of New York, roughly right here, is that there's a transmission line right about, more than one, but right about here that actually bottles the amount of energy transfer available to move from one region to another. So we said, okay, well, what happens if I unbottle that? We increase the transmission capability between New York City and Long Island by 50% to say, hey, what happens? And so what we see here is that, you know, you can see the numbers significantly go down again. So we say, okay, well, the numbers going down actually means that your system is becoming more reliable. So we said, okay, well, that transmission, you know, not improvement, transmission increase in capability have made the system more reliable. Now, again, we look at these numbers and say, wow, but they're pretty much the same across all the different scenarios of offshore wind. So again, we scratch our heads that, well, we need to look in great detail about our numbers, and we certainly did that. And of course, we as researchers wouldn't just stop there because we really need to get to the bottom of this answer. Then we said, well, you know, interconnection points are really important. What if we move these interconnection points? So what we did was, you know, these 2 that are in New York City area, we combined them and just moved it into the Long Island area here to say, hey, like, let's say it's a small change. Instead of interconnecting these 2 red points here, we decided to interconnect the Long Island. You know, what does that look like? And now what you can see here is that the loss of load expectation is about 6.6 in the first hour. First hour as in the first scenario here, the 0 gigawatts of no offshore wind injection. And as you add 2, the number goes down to 1.4, less decimal points, and goes to 7, get a little bit higher here. And let's see. So yeah, so what we see is the LOLE actually decreases over these different scenarios, which essentially means that the system is getting more reliable by injecting the energy directly into Long Island. So, you know, what's the takeaway here? We've looked at a lot of numbers and different scenarios here. is that number one, interconnection points are extremely important. And when I was saying, you know, not just to how the system, how you would interconnect in the system, but when we think about, you know, what is the contribution to reliability, you know, this would have some impacts into congestion as well. This is, you know, this is something really important to look at in your work as well. So for maybe one thing that I missed out here, it is quite historically known that Long Island, as you can see, because its geographic, you know, kind of the end is a little bit more isolated, so its reliability under these metrics are typically lower anyways. But you can really see that, you know, just the difference between injecting 5 miles to the east versus 5 miles, 5 to maybe 20 miles to the west can really make a really big difference for the reliability of the system. Okay, so with that, I am on my summary slide here. And so, you know, I have the great pleasure to present to you today the study of a few of my teammates and myself on this work. Again, we're looking at the potential impact of adding different levels of offshore wind within the Northeast region of the US. And so in summary, you know, a couple takeaways is that we saw fairly low renewable curtailment across the board. So the summary is that, you know, by adding this wind, there's not extensive power system operations changes that we would see. Though they do impact other units, like increased amount of startups and decrease hours online. You know, this is really important, especially for thermal units, because you know, the cost to start up a unit or the amount of time to start up a unit can add quite a bit of strain to the mechanics, as well as, of course, for anybody, right? If you're decreasing the hours that you're producing or online, this certainly will impact your revenue as well. In terms of financial costs, we use the metric called the production costs, which we saw that it may decrease based on our study here, and assuming renewable energy costs at $0, and specifically looking at, you know, 2012 there. The offshore wind interconnected near load centers. This is something maybe I didn't talk about as much. We can talk about here is that you know, in the Northeast, it is quite heavy with population as well as major big cities. Right? I mentioned New York City. There's also Boston in the area there. So you know, one of the perks, shall we say, of offshore wind being so close to the coast is that that's also close to where these major load pockets, load centers are. So by injecting into there, you know, we also saw quite some energy flow changes and changes in transmission congestion as well, which is very sensitive to where you're injecting that interconnection or injecting the energy. So there's a significantly more information in the report on this item as well. And finally, that last slide I talked about, which is about resource adequacy and the reliability, shows that, you know, Long Island has limited resources locally in that transmission import, right? Whether expanding that transmission system within Long Island to New York City, or other options, of course, to its neighbors, as well as maybe considering different interconnection points is, you know, can show a great benefit for reliability there too. And finally, of course, you've heard caveats throughout the study, but I definitely want to be very clear in terms of what we looked at here. So, you know, one of the limitations of this study is that with the models that we use, it's a DC representation. Of course, the majority of the US power systems is in an AC system. So there is some dynamics and stability not looked at here. So to do, of course, when you're looking at interconnecting wind and doing your AC system studies, right, it's much more detailed in terms of the physics there. It doesn't address any interconnection operational requirements either. So again, this is not a cost-benefit analysis. The study does not consider the cost of building and interconnecting wind or any necessary system upgrades. And the final one is that this was a one-year snapshot of that 2012 historical year projected to 2024. So growing the load a little bit, but maintaining the meteorology of the historical year 2012. So it is a one snapshot and can be limited in changing system conditions. Obviously, I don't think anybody could have forecasted this year's load changes and different wind scenarios either. So, and with that, I think I just want to, again, thank you for your attention. You'll find myself and my colleagues, Philip and Josh's contact information here if you'd like to discuss in more detail. But at this time, I think I'll turn back to Carrie, and I'd love to hear any questions and discussions as well.
Thanks so much, Jessica. So as I said at the start of our presentation this morning, if you have a question, use the texting chat box. I know I've seen a couple just come through, so I'll give folks a few minutes to use that, and we'll do our best to kind of methodically go through them. And now, I'm not sure, Jessica, if you can see those or not, but I'm happy to restate them. And I have just two that I wanted to ask, and I think you addressed, but were kind of packed in the presentation. So the first was related to the reference year. So you just mentioned using 2012 as a reference year, but of course, you took into consideration the state mandates and things like that that have been introduced. Up to what point did you use those? What year were they? You know, up to 2019 or 2018? Do you see what I'm saying? You're using 2012 reference year, of course, for load and you know, the system itself. But what about the mandates? Just more specifically, what did you include?
Yeah, no, great point. So I guess just to maybe go through the years again. So we began the study about 2016, 2017. So at the time, very early 2017. So at the time, there weren't the same mandates that we are in now. And, you know, a quick reflection on that is that, you know, when we look at 0, 2, and 7, I think in the year 2020, we'd say, oh, hey, that's a little bit low. I think I think many of us are interested in seeing higher amounts like 12 and 20 and 100 at this point. But at that time, if you can take yourself back a couple of years, that those were ambitious numbers actually for the Northeast. So that's kind of what we're looking at. And at the time, there weren't any installed offshore wind units either. So that's one thing I think to keep in mind here. You're bringing up here that, you know, we don't have those policy mandates included because they didn't exist at that moment.
Okay, very helpful, thank you. And then my other question relates to imports and exports, which I think you addressed, but you went quite quickly. Just how did you handle those? Did you exclude those? So, you know, Canada or PJM, any imports or exports, were they addressed at all?
Yeah. Addressed as in absolutely modeled. So what we do in our system is we actually model the entire Eastern Interconnect, but all the results that you saw, of course, were focused specifically in the Northeast because that's where the region was. So in terms of, you know, New England and New York regions, they were freely to import, export with the other areas as well. And the other areas were also in a 2024 year. So everything is aligned in terms of, you know, a 2012 historical meteorology and load, and then forecasted to 2024. Does that make sense?
Yes, it did. So I'm going to read a question that we received through the chat room, because I'm not sure if you could see it or not. So on slide 15, the person's referring to slide 15, are the second and third scenarios stackable? And then referring to combined additional 50% transmission and move to the POI to Long Island? And would this significantly impact the LOLE value? Might need a minute to think about that.
Yeah, that's a really great point. So, you know, we didn't look at that, these two scenarios stacked together. So they are, you know, isolated in terms of scenarios. I would say that, you know, the reliability, and maybe one of the things I didn't point out is that this reliability number is of the entire Northeast area. So that New England, New York. And, you know, where we saw regionally was that the highest loss of load expectation was all bottled within the Long Island area right here. So, you know, of course, without running a study, but my quick take would be if you were to stack the transmission expansion plus the interconnection point in Long Island, I think you would see some improvements, but you probably wouldn't see it, you know, at this kind of level it wouldn't be like a one-for-one adder, if that makes sense. So you, yeah. Happy to, I think that was from Matthew. Happy to take a follow-up question if that didn't make sense, or if you have any other questions.
Okay, so I'm going to wait a moment and see if we get some other questions in our chat box.
Okay, great. I certainly can see a lot of people have called in today. So, and not to flatter myself, I know there may be better things to do while you're isolated at home, but I think since you've taken the time as well, I'd love to hear about your reaction to the study, what you're seeing here or what your interest is. I think that's, something that would be very helpful to me and the research team about thinking of, other future studies that we do and how we think about the world as well and keeping us grounded. So thank you in advance.
Okay, I'm just pausing for a second, Jessica. So I don't know if you saw this one, Dean, which is a broader question about NREL's efforts in, I think, offshore grid development. So that's a very broad question, but maybe you can talk a little bit about the portfolio that NREL is thinking about or has done in the past.
Yeah, so I guess there's two parts maybe to that question that I'm reading. Is one is sort of like how does our research work with or consider offshore grid development, and maybe the second one is maybe how does it relate in our studies too that we've done. So Carrie, I think you work very closely with Walt Musial, who is from NREL as well, who works in the consortium. So certainly Walt Musial is one of our top offshore wind experts at NREL. So extensively the portfolio, as I mentioned before, expands from different types of technology, fundamental science, all the way up to these type of studies that we talked about today, which is hey, let's assume technically it all works out and it gets built. What are the impacts to the system in a both economical and technical way? So it's certainly, I think, things that we've done for, I know that Walt has been working on this quite a few years, but of course in the past few years, there have been a lot more partnerships in this area as well too. And in terms of our studies, I would say that in the past, so maybe the last 10 years or so, a lot of the power systems or renewable integration studies likely had a lower amount of offshore wind. Just like, when we think about the cost decrease of the technology cost decrease across solar, land-based wind, offshore wind is experiencing that as well. And, 10 years ago, I think where we are now was kind of the pipe dream. But of course, as NREL's mission here is certainly, one in the fundamental science development to decrease those costs actively with a partnership with Department of Energy, but also to make studies like this so that we at least know what the impacts look like. So I think maybe, Carrie, one of the things I can go back and do is work with Walt and pull a couple of resources out about other work we've done in the offshore wind area that may be of interest to people.
Sure, and I'll just add that at the start of the conversation, and if you go back and look at the deck when we send it out in the recording, you'll see that a few of the awards made by the consortium have been to NREL and their subcontractors. So in very different areas from what Jessica's addressing this morning, but more work in wind monitoring and arrays and that sort of thing. So I think it's on that side there. You can see those. You can see NREL has been the recipient of a few of those awards thus far. So that gives you, I know that's not the full picture, but that is a partial picture of some of the work that's gone on. And Jessica, we have another question here that I'll repeat for our audience this morning. What would you hypothesize your results to be if you discarded the assumed substations, the 35 kV buses, and used more small buses in the model? What might the model be able to tell us, and would that be a useful trial?
Yeah, I think it definitely would be a useful modeling effort. With a lot of experienced power system engineers, I think that are very familiar with this area, there's some probably immediate assumptions we can make, but the plus side about modeling is that either it confirms what we're thinking, or a lot of times it introduces some factors we didn't realize before. And so, you know, sometimes, of course, as an engineer, I have some hypothesis coming in, and again, I'm not trying to prove it right. It's more of a exploratory research. But in this case, you know, sometimes I'm surprised by certain findings. When we talked about resource adequacy, that was certainly one of them. I was really surprised how much looking at that transmission capacity within the region and enabling some flows or moving the interconnection point really made a difference. So, you know, when we look at these 345 kV buses here, I think one of the perks, shall we say, of interconnecting at this level is that your capacity is much higher. So the amount of offshore wind, and assuming, you know, some efficiency of lumping in multiple plants together or farms together to interconnect, you might have a little bit of interconnection cost efficiency improved over, you know, multiple smaller ones. So that, I think that would be, you know, one thought there. In terms of injecting energy across maybe many small points instead of these major four of them here, I think is you would see a little bit more transmission congestion, which means that it could drive the prices a little bit higher. The production cost decrease percentages may be a little bit lower. So that's probably one of my initial sense of what may happen. But again, I think you know, modeling and detailed studies are really important, and that's what I'd end with. Yeah. I think just looking at the chat window, I think there was a question about, like, related to that, what might be the model that tells us. So, you know, I think production cost models are a good first step to assess what are the types of scenarios that you're interested in looking in more detail. So maybe treat it as a screening tool in a way. And then models like power flow type models, I think those would be a good next step. And that's, you know, these are the same type of models that the ISOs use as well when they're considering the interconnection studies. So this is, you know, I think using kind of the standard industry vetted models, of course, I think would be highly recommended too.
Great. And I think we have, I'm going to restate a question that's been submitted and add a little bit to it. And then I think we'll maybe let you off the hook because you've been fantastic for speaking for so long. So the question is, can the model or the study that you've just done, do you plan on, or can it be updated to reflect the goals that have been adopted in the Northeast? And then I had a follow-on question for you, which is very broad in its nature, but do you know if NREL is thinking about similar approaches to what we consider for PJM or the Southeast or even off the coast of California in terms of power system planning? Or could the same, maybe even step back from that, could the same type of model be applied to those scenarios as well? Because we're, of course, trying to think nationally. So if you could comment on both of those, that would be great.
Yeah, absolutely. So in terms of the first question about could the model be updated, the answer is absolutely. We at NREL, we maintain a how do I call it, an evolving, up-to-date model data set. So at this point, we originally started about a decade ago in some smaller areas. As we stitched those areas together, you know, we got all of the Northeast, for example, and as we stitched more areas together, we got all of the U.S. And over the last couple of years, my colleague Greg Brinkman led a project called the North American Renewable Integration Study, which stitched together all of the continent of North America. So it's a partnership between the governments of Canada, US, and Mexico in looking at different futures of renewable integration. So I would, that study is probably due to be released sometime this year, probably later this year. So that's something to look out for too if you're interested in this type of study. That one will have a lot of different policy futures and a focus of other technologies as well, since this one is specifically on offshore wind today. So we've, I guess the short answer is yes, we continue to update these models. I think if we were to look at specifically offshore wind again, there are, to do it in the year 2020, I think there would be a lot of updates I would make to our assumptions here, maybe expand some of the, transmission networks that might be offshore that we can consider as well, and those different interconnection points that you guys are all, pointing out as well. So I think those are all good places to start. And, I guess a small plug there is, a lot of our studies, like this one, is funded by the Department of Energy. So the majority, like 2/3 of our work, is funded by them. But the other third, as I mentioned earlier, is that we partner with companies and countries and different entities across the world to look at, energy efficiency and renewable energy, and what is the next thing that people should be thinking about. So we're happy to support that mission. We feel very strongly about it, and be happy to engage on that as well. For the PJM kind of lower eastern coast, I guess, if we describe it that way, there are plans with DOE over the next few years to look at extending the offshore wind study, or extending a grid integration study like this with continued focus in offshore wind on the East Coast. That's in very early stages of discussion at this point. So I don't really have any timelines about when that would complete or things like that, but we are in discussion at this point. Yeah.
Great. Thank you so much, Jessica. I really appreciate the presentation this morning and answering all our questions. Do you mind, I think you have control, do you mind just going to the last screen so we can flash up, maybe do your last screen as well so people can see your contact, and then do the last consortium one, if you can? Not sure if we can get there.
Sure, yeah. Great. This is me here. Yeah, Jessica Lau. Feel free to email me if you want to chat some more about the study or other grid integration or NREL in general. I'm happy to do that. And then we'll go to you, Carrie, here, I think.
So I'll talk while you do that. Thank you all for participating this morning. We had around 70 folks join us today, so that's fantastic. Again, our goal was to present some of the work that NREL's been doing, and hopes to really foster some thinking about what technology research might be needed to help offshore wind reduce its cost in this area related to power system planning and transmission planning. So we're thinking about that here at Consortium, both in terms of and what research we can fund, but also how we work with others and continue that kind of thinking and thought process. So Jessica, thanks for laying kind of a baseline for us to kind of start thinking about that from a technology perspective. And as I mentioned earlier, the presentation, we'll email that out to folks with the audio, excuse me, as well. That'll take us a few days. But then finally, I would like to say that we're interested at the consortium in hearing about what your interests are in this specific area. As I said earlier, this is a challenge area for us within our roadmap. What interests you? What do you think needs to be studied from a technology standpoint and from a research standpoint? And feel free to email me directly. My email is here, and love to get the input from folks on this call. And again, we thank you for your participation, and thank you, Jessica and team, for sharing your study with us. It was fantastic. Thank you.